Just a second. Yes. Okay, we're live.
Excellent.
Okay, so I'll do a brief introduction and then I'll give you the word and you can 50 minutes or something like that. So I'll do a brief introduction and then...
Oh, I can hear some feedback from you, Flavio.
It's like 15 seconds or so. Good. So welcome everyone to the last of this term. Happy to welcome Murray Pollock. So this is actually the third time that giving a talk in our seminar. For the first two, we had the pleasure to have him personally in our department. That's not possible now. So Murray got his PhD from Warwick University some years ago. Then he was also an assistant professor at Warwick for some time, and to Newcastle University, where he is a professor. And his research interests are mainly Monte Carlo methods with a very strong interface with stochastic differential equations. And so Murray, thanks very much for accepting the invitation, and I leave it up to you now.
Thanks, Flavio. Thanks for the invite. I must admit I prefer coming to Brazil, and it's a lot nicer than being sitting in my flat in Newcastle. Okay, so today I'm going to be talking about a bit of work I've been doing with a number of people, mostly with Gareth Roberts, David Steinsaltz, who's at Oxford, and Andy Wang, who's now a postdoc at Bristol. And also we're doing ongoing work with Hector, who's a PhD student at Warwick, who's working with me, and Christian Robert, who I'm sure some of you know. And the work we've got is called RESTORE. It's another acronym. It stands for Randomly Exploring, Stochastically Renewing. That's the acronym. And it should become clear slightly later on why that's an appropriate acronym. So I'm just going to plow ahead. So I found this cartoon online. I think it symbolizes everything about my current life. I'm not actually leaving home at all. I'm just sitting at this desk the whole time. The only thing which is not quite the same as reality is I don't have a swivel chair. I need to try and invest in one of those. Okay, so some of the inspiration behind this work really goes back to PageRank. And by PageRank, I mean Google PageRank, which I'm sure some of you, if you're not familiar with the details, you'll at least have heard the terminology before, or the term before. So PageRank is a reasonably old idea. I'm going to try and describe it to you in a high level and why it might be interesting. So this picture here represents the internet, okay? It's a simplification, it must be admitted. And I've got lots of different aspects to this graphical representation of the internet. So what I want you to imagine here is each vertex is going to be, say, a website. Each edge is going to be some connection between a website or two websites. And what this grey shaded region here essentially is websites that have got some sort of similarity, right? So it could be there between those groupings of websites, there's a lot of connectivity. So for instance, one grey blob might be websites in Brazil and another grey blob might be websites in North America. And so there's a lot of interconnectivity between them, but relatively few, I guess, edges across the different groupings. Okay, so this is a simplification of the internet. And essentially how PageRank works, skipping over a lot of details, is they want to build up some sort of notion of what the most the most popular websites are, right? The most highly rated websites by some measure. And so the way they define this is they have some notion of essentially a random walk on this graph, right? So we would initialize a Markov chain at some vertex, say this website here. And what we would do is we would move from that website to another website which has an edge connecting to that one, right? So for instance, I might move from this website to this website, and then this website to this website, and so on, okay? So essentially PageRank works a bit like, I guess, an early undergraduate module on Markov chains, in that we're working on a discrete state space where we move from one website to another website with some probability. And this probability given by this edge here is some measure of connectivity as given by links between one website and another website. So what they do is really quite simple, actually. They run it for a long time. And so they build up some record, some ledger of where this random surfer, as they call it, has visited, okay? And websites that are visited the most often are given the highest rank. That's the idea. Or another way of thinking about it is what we're going to do is have a Markov chain evolving in this space, and we're going to look at its stationary distribution. And we're going to rank the websites according to the ones that have been most visited. Okay, so there's a lot of analogs with things we might see in early probability courses or some MCMC type applications, in that we've got discrete state space and we're thinking about a stationary distribution on it. Now, you can imagine a problem you might have if you're a statistician in this world. A statistician in this world might have problems running MCMC on this space or a Markov chain on this space, because really it might evolve really nicely in each one of these gray blobs, right? Because there's a lot of connectivity between websites. But you can imagine it getting really stuck going from one gray blob to another gray blob, right? One grouping of websites to another grouping of websites. And the reason that might be is there's relatively few edges that cross these gray regions, okay? So you can imagine running a Markov chain on this, it being really sticky, having a massive burn-in period. It would take a long time to run, okay? And when PageRank was originally proposed, they had sort of quite a neat solution to get round about this, right? So what would happen is a random surfer, right, our Markov chain evolving in this space, would evolve for some period of time, and then would what they call teleport, right? And what do we mean by teleport? So it would evolve for a period of time, and then it would stop evolving, and then jump to some other location on the space, right? And you can see sort of heuristically why that might help. If you've got a Markov chain where you've got these regions which you end up spending a lot of time in without moving across the different groupings of the websites, being able to jump there might be really beneficial to you, okay? So you evolve for a period of time, and with some probability at each iteration, you stop evolving according to what I'll call local dynamics, i.e. looking at the edges beside where I am, and then instead going to some global dynamic, you know, for instance, uniformly choosing a website in some other part of the space. So that sort of works when I'm Google and I'm dealing with this sort of notion of ranking websites, because of course, a ranking for a website doesn't really have any meaning to it anyway. You know, if I modify the behavior of this Markov chain, it's going to change the stationary distribution if you think about it in a statistical term. But in terms of being able to look at the number of times each website's visited and rank them in that way, it's going to give you the right sort of ordering, right? It's going to change the ordering perhaps a little bit, but it's going to give you the right sort of ordering. So if I'm Google, I can really make my algorithm more robust my Markov chain more robust by augmenting local type dynamics with global dynamics. But I don't get the same stationary distribution. And so this type of idea, if you were to apply it to something like MCMC, wouldn't really work, because by jumping to another part of my space at random, I change the underlying distribution I'm trying to target, right? So it's a nice idea if you're a computer scientist, but not necessarily a statistician. Yeah? But you have a behavior which is locally you're randomly exploring, and then you're going to be stochastically renewing, right? You're jumping to some other part of the space. And this is where the acronym is going to come in. Okay, so just to summarize this, PageRank, which is a very popular algorithm, really, it's quite old. I'm not really giving you any new information that's not been around for decades now on PageRank, but it's a really cool algorithm, right? If you think about the dynamics, you have a local random walk component, you do a global teleportation, you jump from one part of the space to another part of the space, and really you're moving between doing local updates and global updates according to some rate. Right? You can think about it being like a Poisson clock or something like this, where you have some teleportation rate. You know, how often I'm going to move from doing local dynamics to restarting somewhere else in the space. And this is where the acronym comes from. Restore, randomly exploring, stochastically regenerating or renewing. So the problem when you come to a statistical context is we're not interested in ranking sites. We're actually interested in choosing the dynamics of our Markov chain, perhaps so it satisfies detail balance or some other trick so that it targets a particular invariant distribution or stationary distribution that we're interested in. This artificially changing the problem to suit the sampling isn't really a valid thing to do. Now, within PageRank, you might think of some natural extensions to it, right? So some things you might naturally want to extend it to is rather than moving like a random walk locally, you might want to move perhaps in a more interesting way, okay? You might want to choose non-reversible dynamics, for instance. Or you might want to teleport out to regions if you've become particularly stuck in them. You might want to have a state-dependent teleportation rate. Or you might want to move somewhere in a very informed way. Okay? So the original formulation of PageRank, it was a local random walk-like behavior. It was a regeneration rate which was constant, and it was a uniform distribution over websites, a particular class of websites. And so you might want to think about extending this in some way. But of course, each variation you do, if you don't do it in a compensatory manner, will change what the stationary distribution is, and so will change the ranking that you get. So you might want to think about modifying these in a way which preserves the original stationary distribution, the original way you thought about ranking websites. Okay, that's a long introduction. So that's PageRank. And really, it's a computer science application. It's not really a statistical application at all, although it uses Markov chains. Okay, so in a statistical context, if we're doing, say, Monte Carlo, we're going to have some fixed target distribution. I'm just going to call it a target of interest, which I'm going to call pi, okay? And either we want to get representative samples from pi or get representative samples from pi so that we can compute some expectation of this form in the usual way, right? So there's lots of different things I could do. I could do, for instance, a simple Monte Carlo algorithm. I could simply simulate directly from pi if that were possible, and then compute various estimators for this expectation if it were possible. But of course, very often it's not going to be possible, and so I would instead use MCMC, right? Very often I would use MCMC. And MCMC is a really cunning trick, right? In that it's a Markov chain, just like PageRank was a Markov chain on some discrete state space. Here I'm going to have a Markov chain, perhaps in some general state space, say RD, if that is the state space of pi. And what I'm going to do for this Markov chain is I'm going to choose the dynamics so that the Markov chain is pi invariant. I run the Markov chain for a very long time with this pi invariance property, and then I use the trajectory of the chain, the evolution of the chain, for the purposes of computing an estimator or as a sequence of correlated draws representative samples from pi, right? That's the key idea. But in this key idea, there is a restriction, and that sometimes in order to get this pi invariant Markov chain, I apply lots of notions which are counterproductive. So one way of getting a pi invariant Markov chain is to choose a transition which satisfies detailed balance, for instance. And this introduces reversibility, and by introducing reversibility, that can actually hinder the properties of the Markov chain, right? So it's a very powerful notion, but it can lead to its own limitations, right? How do you constructively come up with a pi invariant Markov chain? Oftentimes the way you do that causes some issues. Okay, now one of the benefits of MCMC really is it's an incredibly simple algorithm. So let's think about just roughly what the algorithm looks like. So I'm going to fix a number of iterations of the algorithm, say capital T. And in each iteration, I'm going to propose from some instrumental density, say Q, right? I'm going to make a proposal. And then with some probability, alpha, which is a function of perhaps where I currently am and the proposal, I either move to that location or stay where I am, right? So we have this proposal and then a correction. And these schemes are highly tunable, right? This is a very vanilla version of the algorithm, an abstraction which is simplified a great deal, but they're highly tunable. So for instance, there's a whole range of what I'm going to call local and global schemes you could employ. So a local scheme, I'm going to look at information about the target density around about where I currently am in the Markov chain. And the global scheme is it's not going to consider that information at all. Okay, so an example of a local scheme might be, for instance, random walk Metropolis Hastings. I look at my current location and I propose a Gaussian centered around my current location. Or Mala, perhaps use gradient information, or HMC, or even PDMPs. All of these types of schemes I would classify as local. You're using information perhaps in a very informed way or a less informed way about where you currently are. A canonical example of a global scheme in this context might be, say, an independent sampler, right? I make the proposal to my next location regardless of where I currently am. So there's lots of different ways of doing this, right? And not only that, I can think of extensions of these local and global schemes by putting lots of them together, right? So so-called mixture schemes. If I was to create a bag where I have lots of pi invariant kernels, then what I can do, I could put in my random walk scheme, I could put in my Mala scheme, my independent sampler. With some probability, at every iteration, I could just draw from this bag and apply that kernel. And you can think that perhaps that might be a good idea in some sense, in that one of the algorithms might have nice properties, and so by putting it in the bag, I'm going to get a good algorithm coming out of it. It covers all bases in some sense. The limitation of this type of mixture scheme is I've got a bag of pi invariant kernels, right? And a lot of those pi invariant kernels might have been constructed in a way such as random walk Metropolis, which are inherently reversible. A more interesting way to think about this bag of pi invariant kernels is instead, is there some way of coming up with a pi invariant bag? So I'm going to put in lots of kernels to this bag. Each independently might not be pi invariant. They might target some other invariant distribution entirely, which might be advantageous. But if I put them in the right proportion into this bag, the overall bag is pi invariant, right? So can we make the whole scheme more flexible so that rather than thinking about a mixture or a bag of pi invariant kernels, come up with a bag itself which is pi invariant, right? This is a slight reverse perspective. If we go back to the original PageRank, for instance, what we had was random walk behavior and teleportation. And by introducing teleportation, I got a different stationary distribution. What might be interesting is saying, well, I want the teleportation because it's really a really nice feature. It makes my algorithm really robust. So can I introduce teleportation and then rather than using a random walk-like behavior, modify the behavior, it's perhaps not random walk, such that both put together give me the same stationary distribution. So I get the original interpretation of the ranking of websites that I wanted. From a statistical perspective, that's a far more natural question, right? Because I'm interested in the stationary distribution the Markov chain has. Okay, so that would be the goal. But of course, that's a difficult thing to conceive, right? There have been people that have tried it, but it's very difficult. Now, the problems with the local, global, and the original mixture type schemes are really the types of drawbacks you get are sort of the canonical ones that you find in any MCMC application. Oftentimes you've got reversibility, you've got correlated draws, you've got burn-in periods. You have to really tune your algorithm. It can be that some of them are very robust, but only in particular regimes where you have relatively unimodal distributions or have some nice particular properties. The other problem with MCMC actually is if you ever try and parallelize MCMC, you find it's inherently sequential, right? You need to know the whole sequence. If you're running on a computer, you can't run it in parallel because you need to know the sequence X1, X2, X3, X4, and they all depend on one another, in a Markov way, but they still depend on one another. So there's lots of drawbacks to MCMC, such as those that I'm outlining there. Okay. Now, there is a concept within MCMC which is often overlooked, and it's the concept of regeneration. So what is regeneration? Well, it's hard. It involves identifying key parts of your state space where you have some notion of the Markov chain regenerating, right? So things like atoms, small sets, minorization conditions, things which oftentimes when you're studying the theory of Markov chains you encounter, but in practice it's something you don't take advantage of. Now, it is a really nice thing to be able to identify regeneration times within a Markov chain, times where you break the conditional dependency on the initialization and the trajectory of the Markov chain itself. So if you're able to identify regeneration times of the Markov chain, then actually what you can do is you can think about decomposing how you use the output of the Markov chain into IID segments. And if you can compose things into IID segments, then you relieve a lot of the issues that you have in traditional MCMC, right? So for instance, burn-in is an issue, but if you can identify times in which you'd have reached that part of the state space, regardless of where you'd initialized it, somehow you can circumvent burn-in. Okay. So it's a rather technical notion, some of the stuff on the slides, but I want to show you later in the talk how you can take advantage of some of these things. Okay. So restore, what is it? I've talked it up a lot, but what is it? So what we want is we want some fixed stationary distribution, right? Fixed invariant distribution. It's something we're interested in. It comes from some Bayesian model, for instance. And I'm going to try and construct a stochastic process which is pi invariant, right? I've got a fixed pi and I want to come up with a stochastic process which is pi invariant. And I want to have all of these really nice features that we discussed with PageRank, right? I want some local dynamics. Perhaps it's given by a Markov process y, which is not pi invariant. I don't want to do it in a naive way. It's not pi invariant. I want some distribution from which I can regenerate from, right? I want it to be a flexible global regeneration distribution. And I want to have some rate where I regenerate or teleport or kill myself and jump to that stationary distribution or regeneration distribution u. Okay? So it turns out if you simulate the regeneration time in this manner, where kappa is some function and psi is an exponential 1, you can balance y, nu, and kappa in such a way that you still get a pi invariant stochastic process, right? And it's given by finding times, regeneration times at which I jump from the local process dynamics to this fixed global dynamic, fixed global distribution, is according to this sort of rate here. Okay. So kappa has a nice form, and it's perhaps not entirely important for me to go through this in exhaustive detail, right? Kappa's got a particular form, and you can write it down in a discrete state space that has this type of form, where Q is the generator and Q stars is A joint, right? Mu is the regeneration distribution, and pi is your target distribution, and C is some constant such that this is positive, right? So, sorry, I should say Q is the generator of Y, which is the Markov process of the local dynamics. And if you do it in this manner, if you choose kappa to be this rate, then you get something which is pi stationary, if you look at the whole process X. And there's a very simple ergodic theorem, which is just like you would in MCMC, use the entire trajectory to approximate integrals with respect to pi. Here you would use the trajectory to approximate integrals with respect to pi, same sort of manner. Okay. And you can do it for continuous state spaces. It must be said that the Y Markov process, you can think about being as a pure jump process. You can think about being as a diffusion. For instance, if you had a diffusion, this would be the rate at which you did the killing. Or it can be piecewise deterministic. It can be really flexible. Okay. So that's perhaps more than enough details. I realize that technical slides are not most people's. Well, remember it's 5 o'clock in the UK. So for 5 o'clock on a Friday, I don't want to go into the technical details. So let's do some pictures. So what I'm going to do is I'm going to go through the algorithm by a series of pictures. Then I'm going to do coupling from the past. Now, some of you might have heard coupling from the past before, but this is a practical coupling from the past algorithm. And then I'm going to talk about some various constants that we'll encounter when I present the pictures. Okay, so what does it look like? Now, what I'm going to do is I'm going to initialize this stochastic process at some point 0. And for the purposes of this illustration, I'm going to choose the local dynamics to be diffusive, to be like a diffusion. It doesn't have to be, but it makes for more interesting graphs, okay? So what's going to happen is the process is going to evolve for some random period of time, right? It's going to get killed according to some intensity kappa, which I'll discuss in a moment, state-dependent intensity kappa. It's going to evolve according to local dynamics for some period of time given by this diffusive component here. And then at some random time given by this red vertical line, it's going to be killed. And then at that time, I'm going to resample the distribution. I'm going to resample or reinitialize the trajectory by using a draw from this regeneration distribution, which is not state dependent. It's completely independent of my current location, which is nu. So I reinitialize the algorithm. You can think about it, the stochastic process from, say, this point here. And I'm going to simulate it for another period of time, perhaps shorter this time, it dies. And then I'm going to reinitialize the algorithm and do it in lots of little segments like this. So it's quite nice. How would I use the output of this algorithm? Well, what I would do is I would think about using the entire trajectory to approximate integrals I'm interested in. Just like MCMC, I get a sequence of correlated draws. Here I'm going to get a sequence of correlated values, right, given by the local dynamics and the global dynamics of the stochastic process. You can immediately see why this might be interesting if you wanted to try and parallelize MCMC, right? So the process between the times given by the red vertical lines, there's a breaking of the conditional dependency, right? So this point here, the black points, are all independent draws from this regeneration distribution, right? So you can think about immediately, just as I'm presenting it just now, you're getting something which is inherently a lot more parallelizable. The key thing is Y doesn't have pi, it's an invariant distribution. Nu is obviously not pi. I can't sample from the thing I'm interested in, otherwise I wouldn't be using this type of method. But together, using this killing intensity, I'm able to correct for the fact that they're targeting different distributions so that they together target pi. Okay. So there's some practicalities in what I was describing there. So let's go through those in a little bit more detail. So in that case, I've got a continuous time stochastic process. So how do I record, particularly if the local dynamics for this continuous time Markov processor is a diffusion, how do I record parts of the trajectory for use in computing in sets ergodic average? So that's one question. And then how do I compute the state-dependent killing rate? That's perhaps the second question. So we can go back to this. Now, what we're going to do is, instead of simulating a Poisson process of, say, rate kappa, which is a true rate, we find some constant bound for kappa and then do a Poisson thinning type argument. So we propose some killing time, say, here. And then by looking at that point there, we say, will we accept that as a killing time or not? Right? If we accept it as a killing time, I'm going to give by the red line as before, we're going to regenerate. Otherwise, we continue the process as before, right? So you get a whole sequence like this. And what you would do is, because you can't record the whole trajectory, what you would do is you would look at the trajectory at some sequence of points, right? Because you're simulating on your computer, and you would use the output at a sequence of points to compute your ergodic averages. Okay, so here what I've got is green lines represent proposed killing times which were rejected. Red lines denote proposed killing times were accepted. The trajectory is only really composed of continuous segments between the red killing times, and then I'm overlaying it with a whole sequence of blue vertical lines which correspond to when I'm going to observe the process. Okay, so it's starting to look slightly more complicated, and I don't want it to appear too complicated. So what I want to do is just compare it to Metropolis Hastings, right? So on the left-hand side here, I've got Metropolis Hastings. So what do we do in Metropolis Hastings? We choose some initialization of the process. And in Restore, we're also going to choose some initialization for the process, right? Say at time 0, I'm at point X in the space. Then with Metropolis Hastings, I fix some time or number of iterations I'm going to simulate my Markov chain for, right? Say capital T, same with Restore. Now in Metropolis Hastings, at every iteration, I index time by 1, for instance, right? There's going to be a slight difference with the Restore process. The Restore process, I'm going to simulate an interval of exponential length, right? So it's slightly different, right? Rather than incrementing time by 1 at every iteration, it's going to be according to an exponential random variable. Then in Metropolis Hastings, I make a proposal according to some instrumental density Q. The same with Restore. I make some proposal at that time. In Metropolis Hastings, I then simulate a uniform and accept or reject with some probability alpha. With Restore, I'm going to accept or reject with some probability the true intensity over the intensity I used for the next time, so kappa over k. Now, where the real difference is in Metropolis Hastings, if I accept, I move to the new location. If I reject, I stay where I am. In Restore, it's slightly different. If I reject, I stay where I am. If I accept, I jump to a point, IID, from the regeneration distribution. So it looks complicated. Restore looks complicated. But actually, if you think about it in terms of its pseudocode, it's not really more complicated than vanilla Metropolis Hastings, right? But now you've got the flexibility of having local dynamics which are not pi invariant and global dynamics which aren't pi invariant, but which together balance one another out, so you get pi invariance. Okay. So I'm not sure if I've got any questions at this point. This is a good point to answer questions if there are any. I'm guessing not. Okay.
We have a compliment so far.
Okay. I'll take that compliment and then proceed on. Okay, so we've got the restore process. We know what it is. It's very, very similar to Metropolis Hastings, slightly more flexible. Now I'm going to introduce something to you which you'll have either seen before and thought is completely impractical, or have never seen before, in which case, in either case, it's going to be a matter of me going through slowly. Okay. So, as I introduced it before with restore, we start it at time 0 and run it for some fixed amount of time, t. And if t is large enough, because restore is pi invariant, just like you would do with MCMC, you run it for a long time, and then you take the endpoint, and it's approximately a draw from pi. Okay? And it's relying on this notion that t is very large, t is tending to infinity. Right? There's another way to think about this, right? And I'm going to think about it in terms of restore. Suppose at time negative infinity, I'm going to start at time negative infinity, I initialize the algorithm at this black point. And what I'm going to do is I'm going to think about the evolution of this stochastic process from time negative infinity to 0. So from time negative infinity to 0, there's an infinite amount of time elapsed. If I was able to simulate the process from time negative infinity to 0 and look at where the process was at time 0, I would have not a correlated draw, not in the same sense as MCMC, where I've got an exact draw, in a limiting sense. At time 0, I would have an IID draw, right? So it's subtly different if I was able to evolve it from time negative infinity. Of course, that's totally impractical, right? But let's run with this idea. So this is the evolution of the trajectory from time negative infinity to time 0, right? So obviously I'm going to have an infinite number of local segments and killing times where I jump to the stationary distribution mu, right? So the rate at which I kill at any interval of time is going to be, say dt, is going to be kappa, the killing rate, times dt, right? You can think about it like that. Now, what I want to instead think about is, suppose I was able to find some positive lower bound for kappa, right? And now what I'm going to do with my positive lower bound for kappa is I'm going to do some further thinning, another type of thinning operation. What I'm going to do, or coloring operation, what I'm going to do is each one of those possible killing events, suppose the lower bound was epsilon, with probability epsilon over kappa evaluated at this point, I'm going to shade it in with this vertical coloring. Otherwise, I'm going to keep the same coloring, right? So with probability epsilon divided by kappa, I give it this vertical shading. Otherwise, I keep it as it was. So now I've got two types of killing event, but they're subtly different, right? So what's the difference? Well, the red vertical line corresponds to a state-dependent killing rate, right? The state-dependent killing rate is going to be of rate kappa minus epsilon, this constant epsilon that I could choose. This vertical line here is going to be a state-independent killing rate. What does it mean for it to be a state-independent killing rate? It means regardless of where I was in the space, over that interval, epsilon dt, I would have jumped to that point, mu, regardless of where I'd been before. Right? So regardless of where the process was instantaneously before that point, I was always going to jump to that point. And of course, the regeneration distribution is state independent. And so there's no information before that point that influences the Markov chain at that point, or the stochastic process at that point. Okay, so I evolved this from time negative infinity to 0. And I have this whole sequence of state-dependent killing times, where I jump to mu, and state-independent killing times, where I jump to mu. And that's from negative infinity to 0. Now, I know this time here is a perfect draw from pi. So what I'm going to do instead is thinking out, working from 0 back to time negative infinity. So at the time of the last killing event, I know at this point here, regardless of where I initialize the algorithm, at this point here, that's going to be a perfect draw from mu. And then the time before I reach 0 is going to be a random variable, right, which I'm denoting by tau. The length of time elapsed from that time point would be tau. This is still an IID draw from pi, and this is an IID draw from mu. The only thing that's changed is the amount of time I'm going to evolve the process is of length tau, where tau is an exponential random variable. In fact, it's going to be an exponential random variable of intensity epsilon. Okay, epsilon being the lower bound I managed to find for kappa. Okay, but we're dealing with a time homogeneous Markov process. And of course, what I can do is just move everything along by tau, right? So I can think, of course, about initializing the process at time 0 from an IID draw from the regeneration distribution, evolving it for some random amount of time, tau, which is going to be an exponential epsilon random variable, and then simulating a sequence of killing times and local processes and global processes. The only difference from restore before is now the killing times from this red process are going to be kappa minus epsilon. And if I evolve the process for this random length of time tau, what I get is an IID draw from pi. So even though I'm constructing a Markov process, I can still get IID draws from pi. Okay, so what does this look like algorithmically? So the regular restore, right, and I call it restore kappa mu y, kappa being the regeneration rate, mu being the regeneration distribution, y being the dynamics of the local process. If I contrast that with what I'm going to call coupling from the past restore, how did they change? Well, with regular restore, you initialize from a fixed point. In coupling from the past restore, you initialize from the regeneration distribution. Okay. In regular restore, you fix time, whereas in coupling from the past restore, you simulate an exponential random variable. Okay. You then do the same type of proposal for the local dynamics and acceptance uniform that you would have in other settings. The acceptance probability changes slightly, but otherwise the algorithm stays the same. And we output the trajectory. The nice thing about this coupling from the past restore is the trajectory at time tau, the end of this process, is going to be an IID draw from pi, right? That's the real beauty of it. So we can get a perfect draw from the stationary distribution. Okay, so here's some examples. Suppose we had a univariate multimodal Cauchy target, right? I'm going to make the target multimodal by choosing n in this case to be reasonably small. Okay, so that's my target distribution. And it looks like this for the particular data points I've chosen. That's the target density. And what I'm going to do is I'm going to choose local dynamics given by what I'm calling an unstable Ornstein-Uhlenbeck process. Okay? So a regular Ornstein-Uhlenbeck process has mean reversion. It's like an AR1 of minus yt dt, right? The process evolves into the tails and gets drifted back to the origin. Here I'm going to deal with an unstable Ornstein-Uhlenbeck process for the local process. So this process starts at 0, starts moving into the tails, and then starts moving even faster into the tails. It really rapidly accelerates into the tails, right? That doesn't have a stationary distribution, okay? So the local process that I choose doesn't even need to have a stationary distribution. It can do, but it doesn't have to. So you can think about designing Markov chains that locally really move fast into the modes. You can think about it like this. I'm going to choose what I'm going to call mu star. I'll come on to this later. I'm going to choose some regeneration distribution. And obviously, I'm going to choose the rate, given a fixed local dynamic and a fixed global dynamic. The rate I'm going to choose is according to this recipe, which ensures that I get pi invariance. Okay. So this is what the killing rate looks like if you subtract the constant, okay? It has this sort of weird form for this particular target density. And if you run the algorithm using what I call mu star, I'll come on to this in a little bit, this is what you get as the output of the algorithm, right? I mean, unsurprisingly, it characterizes the target density really nicely because all I'm doing in this case is getting IID draws from the target density, okay? So it has the same type of convergence dynamics, or convergence rates and such like as standard Monte Carlo. Here's another example, which is perhaps slightly nastier. So what I've got here is a mixture. My target density is going to be a mixture of 3 Gaussians, right? The Gaussians have different weights associated with them, right? So 1/10, 3/10, 6/10. They're separated by a huge amount, right? We've got one here at minus 22. That's where its mean is. We've got one that's at plus 15. And the variances are completely different from one another, right? So that's my target distribution. Now, you can imagine you do something, you're being pragmatic, you're looking at your output, you've maybe done some very preliminary analysis. You could think about doing some guesswork and guessing where the modes are, right? So suppose I looked at the output and I didn't have really any idea what the weights associated with each one of these normals was, right? I have no idea what it is really, right? I don't really know where the location is, right? So I get this one completely off, minus 22 to minus 29. I've got completely the wrong variance as well, right? So this is really a guess. I know that there's 3 clusters of points, for instance, when I look at the data. So what I'm going to do is I'm going to choose this really rough guess as being my regeneration distribution. This is going to be my target distribution. And what I'm going to do is, rather than diffusive-like behavior, I'm going to have random walk jumps. Okay? I've got a process which is a pure jump process. And again, I'm going to choose the rate such that my stationary distribution is pi. Okay. So just to illustrate this, how different they are, it's all one-dimensional, but red here indicates what the target distribution looks like. Okay? And black is what my regeneration distribution looks like. So you can see that I'm really off. Massively off. You can think about how pathologically behaved an independent sampler with this rebirth distribution as a proposal would be. It'd be really pathological, right? Because you're proposing in completely the wrong parts of the space. So what does the process look like if you have a pure jump? It looks like this, right? So red indicates here killing times. So what you can see is if you just look at the red banding, I'm obviously proposing regenerations near the points of the space given by the black dotted line, the rebirth distribution, right? And obviously, if I propose there, I'm going to die really quickly. But the local dynamics are going to try and jump around where I'm currently rebirthing and find somewhere better, right? So I get behavior where I die really quickly, really often. But occasionally, I manage to hit on the mode. My local dynamics help me out of these global death spots, right? I managed to find somewhere there's some mass. So I managed to jump into a point where there's some mass, and suddenly I get these long segments where I evolve without dying. And I die because I'm going to always die. I have another segment where I have this really rapid death, and then I jump into another period of stability, right? So it's jumping all over the space in a really interesting way. And this is what the output of the algorithm looks like. Okay. So just to give you a recap, this got submitted last year, actually, and it was accepted at the beginning of lockdown, UK lockdown. I don't know when that corresponds with Brazil. There's obviously a lot to be done here still, right? There's mostly a theoretical paper. There's a lot of practical things we can do. So just to give you a recap, what we're managing to do is, if you think about back to one of my original slides, we're coming up with rather than a mixture of pi invariant kernels, we're coming up with a mixture of kernels which is pi invariant. That's the summary of the whole talk. There's lots of things we need to do for the future, lots of interesting directions with this, right? So what do heuristics, tuning heuristics, how do I choose the local process, the global regeneration distribution? How do I think about these concepts such as diagnostics of convergence and such like, and restore in much the same way as you might be interested in them in the MCMC? What is this notion of tuning and optimality? How might you apply this in a Bayesian setting? I've described to you random walk-like behavior, Brownian motion-like behavior for the local dynamics, even pure jump local dynamics. But you can imagine doing stuff like PDMP-like dynamics locally, for instance, non-reversible dynamics. There's many ways you could perhaps think about doing practical adaptations of the Markov process as it evolves, because you have this natural conditional independency of the regeneration times with previous regeneration times. There's some scope to do that. I don't want to touch on this too much, but you're working in continuous time, so lots of these tricks or problems you might have in things like pseudo-marginal MCMC in continuous time get alleviated. So there's some benefit of working within this regime. And there is some strong connection with work I've presented at UFMG before, but I don't want to present that now. So it's connected in some way to scale, rescale, QSMC, which I've talked about before. Okay, questions? And Flavio warned me that there's a delay between questions.
Yeah, apparently it's not more than 10 seconds. So, do we have any questions for Murray? I have quite a few if you don't have questions. Okay, I'll start asking, and if other people have questions, I'll just show them. So in order to compute kappa, do I only need the closed 4-4 Q and an unnormalized pi? And mu?
So the way we've been thinking of it is, so you basically got 2 degrees of freedom, right?
Yeah.
in the sense of you can choose to fix two things and then the other one's given. That's what the balancing is. So we've always been thinking about it in terms of choosing the local dynamics, choosing the regeneration distribution, and then working out what kappa was to ameliorate that. And perhaps that's not the only way to do it. It's the only way we've really been thinking about it. Maybe it makes more sense in many settings to choose what type of kappa you want and reverse engineer what the local and global dynamics are. So the way we've been thinking about it is the global dynamics are something that you would choose. So you could, for instance, think about perhaps you've done a really quick and dirty Laplace approximation to your target distribution. The way we'd think about it is you would choose that really quick and dirty approximation to be your regeneration distribution. And then what this algorithm's doing is it's sampling randomly from that quick and dirty approximation. And what it's doing is it's doing microscopic perturbations of the trajectory around about that point. You have this notion of, independent segments between regeneration times, right? So you can do a lot of these things in parallel. The local dynamics, we've not got massively good intuition for how to choose them, right? So there's various things that we've been looking at, just purely random-like behavior. That's obviously one thing we could do. The nice thing about the random walk-like behavior is, in this setting, the regeneration distribution together with the regeneration rates, what's compensating you, rather than something like the Metropolis Hastings kernel, right? So you're avoiding some of the issues you sometimes encounter with that. The other things we've been trying, one of the things Hector's working on is what types of approximations of the target distribution have nice behavior for algorithms such like HMC, right? And can you embed these things within it? Then you've got the real issue really is once you've chosen that recipe, then you need to compute what this killing rate is. And it's the same thing with all of these types of continuous time algorithms that rely on killing rates. You need to be able to find nice bounds for them. That's a real limitation for it. You need to find discount constant, so it's always positive if you're working within this methodological regime that we've found. So really a lot of these constants are problem dependent, and it's not really something we've got good answers for because we don't even have a good notion of, right, for a fixed pi, for a whole class of local and global dynamics that we could choose, what is the best thing to choose? Is it really the case that the best regeneration distribution is actually the target distribution or an approximation to it? We don't really know because we don't have a good concept of what rejects. So you would think from one perspective, having a massively more flexible class of algorithms that you can use for your problem is advantageous, but of course, it just means you've got massively more tuning parameters in some sense. And so this is a long way of saying I don't have an answer to your question, but it's got all the same sort of problems that you might ordinarily have in said exact algorithm, these types of things. You've got to find bounding constants, such like. The nice thing about this is you can choose local dynamics, which are non-diffusive. So you can find, you can find less complicated ways of finding bounding constants and such like. Does that answer your question or not?
Yeah. And how harder do you think it gets when you increase dimension? I mean, does it get much harder to choose these things, or it's more or less the same idea, but computation is much harder?
It's a good question. Well, we know that sort of the independent sampler gets pathological with increasing dimension. We've got some hope that this is slightly less pathological in that the local dynamics will be
thinking about infinite dimensional applications.
Well, it's not something we've studied, and it's likely to fall into a lot of the same bear traps, to be honest. Some interesting things, if I just go back a few slides. So this is what the killing rate looks like when you've got a diffusion as the local process. Ignore some of the mass here, right? So ignore what the exact form of the local process is. really the important thing is this killing rate. And the killing rate has two parts to it. It's got a part which is determined really only by the local process and the target distribution, that sort of term here. And we've got another term which is governed only by the regeneration distribution in the target process, or the target density, right? So CAP is additive in these two terms. And what CAP is doing is essentially it's saying to the process, right, if CAP is very large, it's saying, I'm the really poor part of the space, actually there's not much mass here under pi, let's kill the process, I'm better being back at mu than where I currently am. You can think about if the process had a personality, that's what it would be doing, right? Now, the interesting thing is if you were to think about like a pure rejection sampler, for instance, what the acceptance rate of the algorithm is, the acceptance rate for a pure rejection sampler looks like your target pi divided by a constant multiplied by, let's call it your proposal distribution. It would be the same sort of thing in our context as being the regeneration distribution. So it would be something like pi over mu. Here, the way the killing rate appears, where mu appears in the killing rate, it looks like mu over pi. This gives us some hope that actually this class of algorithms, the flexibility of having non-pi invariant Markov processes for the local dynamics might actually be really interesting in terms of the regenerative dynamics, in the sense that whereas in something like a rejection sampler, you want something with heavier tails than your target distribution, here there's some intuition which would suggest that actually you want your regeneration distribution, i.e. your instrumental distribution, to have lighter tails than your target, right? And somehow what the local, because otherwise this is going to explode this term here.
Yeah.
And then really what you're doing with your local dynamics is saying, well, I'm going to start from a point and move out, right? So it gives us some intuition in the types of things that might be interesting. But in some real sense, it's fundamentally different from, even though it looks like a rejection sampler, right? You know, rejection sampler gives you IID draws, this gives you IID draws. We have in a rejection sampler an instrumental distribution and acceptance probability. Here, you could abstractly think about it the same way, but there's something fundamentally different about it, and the role these things play is slightly different. Like local dynamics really give you something that using an instrumental distribution by itself wouldn't.
I see. Okay, last question. What was the computational cost for the examples that did you parallelize them?
So I didn't have to do this is the benefit of being slightly older. I didn't have to do any of the simulations. I don't know. The paper that appears, I should put up the first slide again.
The last one was 3 million iterations, was it?
Yeah, I mean it's all done in a single computer. You know, in principle, you could parallelize all of this. There's details in this archive. There's an updated version of the archive which has got the corrections based on the referee reports. You can have a look at that. So if you're interested in, so we do report it somewhere, it's there. But it is more of a probability paper rather than a methodology paper. The idea of this work is to answer some of these questions like, how do you choose the dynamics? What's good guidance? What's it mean to have a whole class often giving you the right answer? Which one should I choose out of that class? How does it scale with dimension? These types of questions that are very good that you're asking me are things we want to write papers on eventually. It's the framework. I think really the story is the page rank type story, right? It's can you come up with a pi invariant bag of kernels rather than, you know, a bag of pi invariant kernels.
Yeah, it's really interesting. Thanks a lot. We don't have questions from the audience. We have another compliment. I'm sure.
Very good. Thank you.
Yeah, so I think this is it. I want to thank you again, and hopefully we can have even a seminar in person.
Yeah, I hope I can give the same talk in person.
Yeah, which means bad things will have gone away, right?
Yeah.
Okay. Thanks very much. Thanks everyone, and see you next term. I just end the broadcast.